Hi, NA Physics, it's Mr. Neff. Hey, I'm going to go over that second problem set now from projectile motion. First one's number 50. It says a diver runs horizontally off the end of a diving board with an initial speed of 1.85 meters a second. If the diving board is 3 meters above the water, what's the diver's speed just before she enters the water? Okay, so when she enters the water, she's going to be moving two-dimensionally. She's going to maintain the x velocity that she had the whole time. And so if she had the 1.85 meter per second initial velocity, then she's going to have 1.85 meters per second in the x direction the whole time. Even if it were a spot partway in between, it would still be that 1.85 meters per second. Now in the y direction, though, she's going to gain more and more speed. And I can figure that out pretty easily with the kinematic equation. You can see what I did here. I have final velocity equals initial velocity square plus 2 times acceleration times displacement. So I put in the numbers that they gave me. I got a final velocity of 7.668. So now that's not the answer. That's the y component of her velocity. So she's moving forward 1.85. She's moving down 7.668. And so I used Pythagorean theorem to put those two together and get 7.89 meters per second for her speed. I don't need to calculate the direction. They just asked for the speed. On 85, there's a two-dimensional baseball throw. This is a fairly easy one, though, because they gave you the time, and so you don't. A lot of times on these problems, you have to solve for the time. This one, you didn't have to do that. So the shortstop is throwing to second base, and as he throws, the ball is going to drop, of course. And so you can see A would be the gravity-free path, and B would be the real parabolic path. So the ball's thrown horizontally 22 meters per second. They later ask, how far were you from the second baseman? Well, in the x direction, there's no acceleration, so you can see what I'm going to do there. I'm just going to say displacement is velocity times time. So there's my 22 times my 0.45. Both of those were given. And so put those together, and you're going to get 9.9. Now, the second part, how far is the distance of vertical drop A to B? Well, that would be how far does anything drop in the 0.45 seconds. And so since it was thrown totally horizontally, the initial velocity times time term goes away, and that's just have half of the acceleration times that given time squared. And so it drops almost a meter, 0.99 meters. This number 86 about the crow carrying the clam. The crow is flying horizontally, and it releases this clam, and so the clam is moving just horizontally to start. Now they ask, what is the horizontal component of velocity and the vertical component? Well, the horizontal component is going to be the same throughout. So if I wanted to illustrate that, I'd trace that vector a couple times, and I could just show you at every spot, including the end, right where it's about to hit. It is that same 2.7 meters per second. There's no acceleration in the x direction. Now the vertical component, a little bit different. So in the y direction, we have an initial velocity of 0. Remember, it's just going horizontally. An acceleration of negative 9.8 meters a second squared, and the time of 2.10 seconds. So to get the final velocity, it's actually really easy. It's going to be that final velocity equals initial velocity plus acceleration times time, 0, and negative 9.8 meters a second square times 2.10 seconds. When you put that into your machine, you get 58 meters per second. We're just going to round that to two significant figures, make that 21 meters per second. So if I wanted to draw that to scale, I'd have to draw that vector 10 times bigger, and there it is, 21. They only ask for the component, so you don't have to put that together. Had they asked for the final speed, then you could find this hypotenuse right here. And if they asked for the final velocity, you'd have that in addition to that angle right there. A lot going on here in number 90. Fairgoers ride a Ferris wheel with a radius of 5 meters. The wheel completes 1 revolution every 32 seconds. So what's the average speed of the rider on the Ferris wheel? So average speed, as you know, is just distance divided by time. So the distance around the Ferris wheel is the circumference. So you remember that we calculate that as 2 pi r divided by the time that it took to go around. Later on in the course, we'll call that the period of the motion, the time to do one cycle. 2 times pi times 5 meters and 32 seconds down here. When you put that into your machine, you get 0.9817 meters per second. We would round that to 3 significant figures. So there's part A for you. Now, part B uses that. If a rider accidentally drops a stuffed animal at the top of the wheel, where does it land relative to the base of the ride? So here's the thing. At every spot along there, the velocity is, well, which is the size of that average speed, is going to be tangent to this. So it's going to be like so. Maybe for this isn't part of this problem, but it would be like this down here, and this isn't part of the problem, but it would be like this. And all of these red vectors that I'm drawing are, number 1, tangent to the circle, and number 2, 0.982 meters per second. So what I really have here is I have a stuffed animal that's starting off at 0.9817 meters per second, totally horizontally, because it's at the very top of the ride. And so then they want to know, where does it land? So how far out does it hit the ground? Okay, well, I need the time. So I'm going to say in the y direction, the displacement is going to be a negative 5 meters, 5 more meters, and they said this is 1.75 meters down here. So that's going to be 11.75 meters is when it hits down here, it's 11.75 meters below where it started. Now, the initial velocity in the y direction is 0. Acceleration, of course, is little g. And so I got 3 of these things I should be able to solve for the time. And so I'm going to say, notice too, please, that the final velocity is not in this problem. So that shows me what equation to avoid. And I'm going to say delta y equals VOT plus a half AT squared. So initial velocity is 0, which is nice. And so I'm going to rewrite this mathematically. I'm dividing by the a, which is little g, okay? And there it is. So now I'm just going to take and put 2 times negative 11.75 meters and then negative 9.8 meters a second squared, like this. When you put that into your machine, you end up getting a time of 1.549 seconds. And then in the x direction, we know that delta x equals VOX times the time. Sure, technically plus 1/2 AT squared, but there's no acceleration in the x direction. So all I have to do is take my velocity in that x direction, that's what I found at the very beginning of the problem, and multiply it by the time that it's going to go forward and go down at for the same time. And when you put that into your machine, you end up getting 1.52 meters forward. There you go.